Hello people, welcome to Gurukula. I'm Jai. I'm working for R.M.K. College of Engineering and Technology for the Department of Electronics and Communication Engineering. So here in this communication networks lecture video series, we are seeing the various concepts that are related to communication networks. And whereas in our previous video, we might have covered the functions of data link layer, and especially we might have discussed in detail about the physical layer addressing. If you have not yet watched that particular video, I will leave the description on the I button on the top right corner, and I also leave the link in the description section so that you can check out the video over there. So today in this particular video, we are going to talk about a special topic, that is what we call it as error detection and error correction codes. So we will first of all discuss what is the need for error detection and error correction codes, and then we will see what are all the various types of codes that are available for error detection and error correction. And then finally today in this video we will take up one or two error detection codes, and then we will try to see how it actually works in the algorithmic perspective. So without any further ado, let us get into the topic. So first of all, before directly diving into the topic of what exactly error detection and error correction codes are, we are very much interested to know the need for error detection codes. Actually, why do I need a separate code for detecting the error and as well as the correcting the error? So because in the most of the reliable applications that we see on internet, we are sending and receiving the data over an unreliable transmission medium, which means the data which I sent over the internet may prone to lots of noises that is available in the external atmosphere, and all these external atmospheric noise and internal noises will add together so that it may corrupt our signals whatever been transmitted from source node to the destination node. So this is where exactly the data whatever we are transmitting may tend to get corrupted. So corrupted is actual value may be 1, so it may be corrupted to 0. So in the vice versa may also be possible. So anytime data that are transmitted from one node to another node, they may corrupt it while they are in transit or they are in the passage. So that is where actually the error comes into the picture. So there are many factors that can alter the one or more bits of the messages. You may have chances for even one bit getting corrupted, or there may be multiple bits that is getting corrupted. Alright, so however, some applications require a special type of mechanism for detecting and as well as correcting the errors. So in order to ensure or in order to minimize the amount of errors that is occurring in the packets that we are sending from source to destination, we need a special mechanism, and that mechanism is what we call it as error detection and error correction codes. And fortunately, the data link layer will take the responsibility of the detection of error, and in some cases few codes can able to correct the errors as well. So as the class progresses, you will know a clear-cut differentiation between error detection and then the error correction codes. So now we will see what are all the types of errors that is available. So before selecting which type of error detection code or error correction code we have to implement on the system, it is very much important to understand what are all the types of errors that is available on the transmission. So there are broadly two types of errors, out of which the first one is single bit error. So what is single bit error? So single bit error is the term which actually means that it affects only one bit of the given data, which means either 1 can be converted to 0 or 0 can be converted to 1. So that error is what we call it as a single bit error. And whereas on the other side we have the burst error, and whereas burst error represents when 2 or more bits are getting corrupted. So when you look into this particular picture, it will be very clear for you. So this is a single bit error scenario where only one particular bit is corrupted to 1. So this is what we call it as, and all other remaining bits remains as such as it is transmitted. This is the transmitted frame and this is the received frame. As you could observe, all the bits have been received as such except this one particular bit. So this scenario is what we call it as single bit error, since there is only one bit that is corrupted. and on the other case this diagram is representing the burst error. So burst error, as you could clearly see, there will be more number of bits that is getting corrupted. As similar to your previous concern, this is your transmitted bit and this is what your received bits are. So as you can clearly see that there are more number of bits that are getting corrupted over here. So if more number of bits have been corrupted here, then that scenario is what we call it as the burst errors. And in most of the practical situations on our communication network, we might experience only the burst errors. So the reason behind why we always experience a burst errors instead of single bit error is because of the time duration of the noise signal will be higher than the time duration of a 1-bit signal. So definitely a noise signal will not affect only one single bit, but in turn it will affect a sequence of bits, maybe 2 to 3 bits at a time. So this is where exactly we are experiencing more number of burst errors instead of single bit errors. So how do I rectify this particular errors? So in order to detect the error or in order to correct the error, we need certain types of codes or special codes to identify and to correct the error. Those codes are what we call it as error detection and then error correction codes. But a common thing that is available in between error detection and error correction codes are a concept of redundancy. So let us throw some light on what redundancy is. First of all, we will understand what redundancy is and then let us proceed with our further topic. So when you look at this particular picture, so this is a normal Colgate toothpaste that we buy in our home. Have you ever seen this kind of color markings that is appeared on your toothpaste over here? You can see black, green, red and blue. So these kinds of color markings will be there on the toothpaste things. So why is it actually printed on my toothpaste? Am I going to get any useful information out of it? So few might say that this particular color markings will tell us the chemical composition that is present in the toothpaste, but actually it is not. So these color markings are not to represent any chemical formula or any chemical information that is present in the toothpaste. That will be available at the backside or some other places. But what these color blocks does, these color blocks does not convey any information to us, but still these color blocks are being printed on this particular toothpaste cover so as to tell a machine which actually made a cut over here. So whenever in an automated machine, whenever an optical sensor detects this particular color, then it crimps the particular tube over here. So this information does not carry any useful content to the human beings, but this information is meant only to the automated machines to inform that I have to cut the toothpaste tube over here. But instead, when you take this particular symbol, so you can see there is an square type and you have a circle over here which is shaded green in color. This information actually carries an information for the human beings, conveying that this is completely vegetarian product and no non-vegetarian content is included in the manufacturing process of this particular toothpaste. And whereas if there is any non-vegetarian included, then it must be red in color, and if there is any addition of eggs, it must be brown in color. This is for your information. So we have nothing to do with this, with the communication networks. So what I all wanted to try is, the point what I am trying to drive over here is the concept of redundancy is nothing but the addition of information to the existing data units. Alright, so let me put up another example over here. Have you ever seen these colorful dots at the bottom of the newspaper that we buy every day? So why is these colorful dots used for? Why is this printed on each and every single paper of the newspaper? So these colorful dots are to represent that these are all the various colors that have been used for printing of that particular page. In case if there is any toner that is not properly functioning, if there is a blue is not there, then that represents the blue color is not being used in printing this particular paper, so that the color reproduction will not be that much efficient. So this is for the purpose of the printing purposes, and this does not carry any information for the consumers that use or buy this particular newspaper. So even if I cut this part of information, this is not going to affect the data what I am going to study, because we are very much intended about the news and then the content that is present over here. So this is what actually we call it as data. So this is what we are actually intended for, and these are all the additional informations which is actually added so as to check whether if there is any error occurred in this particular data or not. So here in this case, this additional information that is added is what we call it as redundant information. So now let us try to put it on the text. So the process of adding redundant bits to the data is what we do for error detection and then the error correction. Now the term redundant, what that actually means? The redundant is nothing but the data that are able to be omitted without any loss of information or without loss of any meaning on that particular thing. So as in both the examples, in the first example, even though if the color is not properly printed or even if it is not at all printed, we the consumers are not going to get affected because of it, because we are more intended on all the required informations that we need about this particular toothpaste is clearly printed on the some other part of this particular tube, and we will not get any useful information out of it, and this is not intended for consumers or human beings. And as of second example is concerned, this redundancy bit does not carry any useful information for the end users. This is only for the purpose of the print purposes. Right, the printing publishers or the printers, those people will be bothering about this particular color representation. Other than that, the last final consumers or the end users will not be bothering about what information all these color circles are there. So in this cases, these color circles are what redundant information. So removing this redundant information will not going to affect any of the data that I require. So this is not going to alter any of the information that is available in the paper. So this is the actual meaning of the redundancy. So even in the error detection and error correction codes, we are going to add few additional bits. Those few additional bits are what we call it as redundant bits. So we are going to add some redundant bits. Let us assume that this is the sequence of ones and zeros which I am going to transmit from sender side to the receiver side, and this is what we call it as the redundancy bit, and whereas these things is what we call it as the data bit. So at the transmitter side, I am going to add few redundancy bits which will help us to detect if there is any error in this particular block or not, and there at the receiver side, this redundancy bits will be removed from the data bit, and only the data bits will be taken for the further processing. And remember, the important property of the redundant bit is it should not alter the information, or it should not alter the meaning of the data bits over here. So addition or removal of redundancy bits should not affect the data bits at any point in time. So that is what the very important parameter for a redundancy bit. So in most of the error detection and error correction codes that we are going to discuss further will be adding the redundancy bit. So with this brief introduction to what redundancy bits are, we will see what are all the various error detection and error correction codes that are available over here. So before getting into the types, it is important to clarify what is the difference between error detection and then the error correction codes. It is straight and simple. So error detection codes are the codes which is going to tell you that the received sequence of informations has error or not. That's all. It will just tell you whether the received bits is in error or not. Only that information you will get from error detection code. And whereas on the other hand, you have error correction codes, and whereas error correction codes will tell you will not only tell you that the errors have been corrected, it will also automatically correct the errors whatever been there in the messages or not. So that is the only difference between error detection and then the error correction codes. So what are all the types of codes? We have different sets of codes for detecting the error, and we have different sets of codes for correcting the errors. We will see one by one. So first of its type is the parity bit, which is for detecting the errors. And the second type of code for detecting the error is checksum, And the third type of code that is used for detecting the error is cyclic redundancy check code, and in short it is what we call it as CRC codes. Fine. So today in this video we will be focusing more on discussing these two error detection codes in detail, and whereas the subsequent videos we will be discussing about the cyclic redundancy check and then some other codes that we are going to see for error correction as well. So the codes that we have for error correction codes are, this is Hamming code. We are going to take I can say that we are going to touch the Hamming code only a little bit. We are going to take only one or two examples over here and not the mathematical background of any of these particular codes. We are just focusing on the algorithmic part of all these error detection and then the error correction codes. And again, to stress, in this video we are going to see only the parity bit and then the checksum. So let us jump into what parity bits are. So in parity bits, they are broadly classified into two types. One is even parity bit, that is one dimensional parity bit and then two dimensional parity bit. So what happens in one dimensional parity bit? So as you could see over here, this is what my message signal is. This red color marked area is what my message signal is, and this is what my redundancy bit is. And in general we call this as parity bit, that is what mentioned over here. So parity can be of two types. One is even parity system and another one is odd parity system. So in even parity system, putting your data bit and as well as your redundancy bit, the total number of ones must be even in number. So that is what even parity system says. And whereas in odd parity system, the putting together your data bits and then the redundancy bit, the total number of ones in the code word must be odd in number. So as you could see in this particular example, we already have two number of ones and then the parity bit is 0. So we can say that this is an even parity system. So addition of only one bit in front of the data bit is what we call it as parity bit. And since we are adding only one bit for this particular parity word or this particular code word, that is why we call it as one dimensional parity. And there are certain drawbacks or downfalls for this particular parity bit is concerned. So what is that? In case if there are 2-bit errors occurred, so let us take for an example, the first two bits have been changed simultaneously. This 0 becomes 1 and then this 1 becomes 0 and all other bits remains as such. So now the system knows this is what my data bit are and this is what my parity bit is. Correct. So even now I can see that there are two number of ones, which is even number of 1, and still my system says that there is no error in the received signal, so which is actually not correct. So that is actually the drawback of one dimensional parity bit. So in order to come out of this particular problem, we have migrated to another parity bit concept, that is what we call it as two dimensional parity. And whereas here in two dimensional parity, what we do is the concept remains the same, but instead of adding parity bit for only one particular block of data, we will be adding parity bit in two dimensions. One is in the row. As you could see, whatever the data which I wanted to transmit, I will arrange it in row and column fashion, and then for each and every row I will add a parity bit. As you could see over here, I have 6 columns together, so all 6 columns will have a separate parity bit, and the parity bit that we have followed here is even parity system that we have followed. As you could see, I have 3 ones. So as per the even parity system, total number of ones must be even in number. So in order to make the total number of ones even in number, my parity bit should be 1. So that is why I have mentioned 1 is over here, and the same concept applies for all the rows as well. Now this is what the first dimension is. So first dimension is row and the second dimension is column. So this is the second dimension. The second dimension is column. As you could see, there are 1, 2, 3, 4, 5, 6 and 7 columns are there. So 7 columns, each and every column will have a separate parity bit. So 3, 4, 5, 6 and 7. So each and every column will be assigned a separate parity bit, and this row is also assigned another parity bit. So now this type of two-dimensional parity can detect up to 3-bit errors, and sometimes it can also detect a 4-bit error as well. But what is the drawback of this particular parity bit system? Whereas here in this particular parity bit system, there are 14 bits of redundant information that is required just to detect the presence of any error or not. Also, it is carrying only 42 bits of information. So, just to send a 42 bit of information, it is required to send a 14 bits of additional information. So, a total of 56 bit is what we have to transmit so as to ensure the proper error detection over here. So, we must follow a trade-off between the total number of bits that we are using for the redundancy bits as well. So, that is why we go for another mechanism. So, that is what we call it as checksum. So, checksum, this method purely uses a summing algorithm, and the basic idea behind this method is to add up all the words that are transmitted and then transmit the result of that particular sum. And next step is to increase or to find out the checksum over there, and then the receiver performs the same operation and compares the result with the checksum that is being transmitted. So, let us see checksum in action now. So, this is a basic algorithm for the checksum. So, let us see how this algorithm works. So, first of all, at the sender side, whatever the information that I have, that has to be divided into m bit informations, and then I will put as many m bits information, and then all these m bits information will be fed to an generator, and this generator will run an algorithm, especially transmitter algorithm, and then that will create a particular value, and that value is what we call it as checksum. And this checksum value is appended to the data bits, and then the data bits plus this checksum will be transmitted over an unreliable channel. And there at the receiver side, both the data bit and as well as the checksum will be fed to the checker. So, this is what my data bits are, and this is what my checksum is. Both my data bits and checksum is being sent to the checker. My checker will extract only the m bits of information that is present in the checksum, and then it will check if it is all 0. Once it is all 0, then the data is accepted. If it is not all 0, or if there is any non-zero values occurred, then it identifies that there is an error. So, we will see what are all the various steps that is present in transmitter algorithm and as well as the receiving algorithm. So, we will see algorithm in step-by-step fashion. At the sender side, initially the message is divided into m bit words. Once it is done, the value of checksum word initially is set to 0, and then all the words including checksum are added using one's complement addition, and the sum is complemented to get the checksum, and then the checksum is also sent along with the data. So, this is what the sequence of steps that is occurring at the sender side algorithm. And what happens at the receiver side algorithm? Whatever the message that has been received is divided into m bit words including the checksum. All the words that are added using one's complement addition, and the sum is complemented to get the new checksum, and this new checksum is 0, then the message is accepted, otherwise it will be rejected. Now, we will take a numerical example so as to understand the process of this checksum in a very detailed way. So, solving this particular problem will help us to understand the in-depth steps that is happening at the transmitter side and then the receiver side. So, let us assume that the data which I wanted to transmit is 7, 11, 12, 0 and then 6. Let us assume that this is the message which I wanted to transmit from sender side to the receiver side. So, first step what will I have to do is I will have to put all the values into m bit information. So, how do I choose that m bit? M bit can be a maximum number of bit that is required to represent this particular value. So, I will have to choose the maximum value in this particular sequence. The maximum value is 12. So, it is very well known that I need 4 bits of information to represent this particular 12. So, what I will do is I will represent all the 7s and 4 bits of information, and even my checksum should be in a size of 4 bit. So that is what the very first step which I will perform over here, and the second step is I will initially allocate the checksum value as 0 over here. And once that is done, what I will do is I will add all these values. So 7 plus 11 plus 12 plus 0 plus 6 plus 0. So adding up all these values will give us to a total number called 36. So if I represent 36 in binary information, then I will get 100 100. I have represented 36 in binary form. And we already know that we are going to represent checksum only in m bit size. The m bit here is the value of m here for our example is 4. So what I will do is I will keep only the first 4 bits, and then I will successively add these 2 remaining bits to this 4 bits itself. So adding this 10 to the remaining 4 bits, I will get 0 1 1 0. So if I convert this to decimal, I will get 6 over here in decimal, and this 6 is what actually represented over here. So this 6 is what I got after performing the ones complement addition, and then you will have to complement this particular value. You will have to take ones complement of this particular value to get the checksum. So if I take ones complement, I will get 1 0 0 1. So this, if I convert to decimal, I will get 9 over there, and this 9 is what is nothing but that is what my checksum is. That is what represented over here, and I will have to replace this 9 in place of 0 before transmitting my signal. So see, 7 11 12 0 6 is the data, and in addition to the data unit, this is what my data bits are, and in addition to the data bit, I am adding my redundancy bit as well. That is my checksum. That is, I have added 9 and then I have transmitted over here. So this is what actually happens at the transmitter side. So what happens at the receiver side? So there at the receiver side, the procedure remains the same. I will have to put all the received bits in sequence, and then I will have to take only m bit. The m bit that we have selected over here, over there at the transmitter side is 4 bit. So even at the receiver side, I will have to go for 4 bit over here. So what I will have to do, I will have to add all these values, and adding all these values will give us an total sum of 45. So what is the next step? I will have to represent this 45 in binary. So if I represent 45 in binary, I will get 10 1101. So we very well know that the checksum should be only in 4 bit. So I will keep only the first 4 bits, and then I will successively add this 10 to my next row. So I will add 10 over here. So I will be getting 1111. If I convert this to decimal, I will be getting 15 over here, and that 15 is what represented here. So this is the value which I am getting after performing ones complement addition. And in order to get the checksum, what I will have to do, I will have to complement the ones complement added value. If I complement this, I will be getting all zeros. Converting this to decimal, I will get 0 over here. So that is what represented over here. So now it is very clear that I have received a checksum value of 0. If the checksum value is 0, then that represents there is no error in the received data frame, and so that all the data whatever been received is accepted, and then it is transferred for further processing. So you can calculate, I will leave it as an assignment or for your exercise at this particular point. What you can do is you can change any one value. Instead of 7, you can replace it with 8, which means you are manually introducing the error in the received bit stream, and then you can perform the same receiving algorithm over here, and you can clearly see that you are not going to get any non-zero values here. You will be getting a non-zero value here, and that represents that the checksum has successfully detected the errors. So this is how the transmitting algorithm and then the receiving algorithm of checksum will work, just to detect the error that is happening in the received stream or not. So coming to the pros and cons of checksum, this algorithm is far better than the parity bit algorithm, as the redundancy bit, we can use a maximum of 16 bit of checksum. 16 bit checksum is more than enough for any length of data that we can transmit. So a 16 bit of redundancy is more than enough to detect the errors, and that is a very good trade-off between the number of bits in data and the number of bits in the redundancy. And the downfall of this particular checksum is they do not provide a proper error detection if one bit increases by some value and the other bit is also reduced by the same value. So in our example, we said that we are going to transmit 7, 11, 12, 0, 6 and then 9 including the checksum. In case in transmission, let us assume that this 7 is converted to 6 and similarly this 11 is converted to 12. So remaining bits I have received as such. So when you sum all these values, I have introduced the error over here. As you could see, 7 is reduced to a value of 1 and then 11 is increased to a value of 1. So if I sum this particular group of values, I am going to get 45 and similarly I am going to get 45 for this set of values as well. So this type of case, my checksum will not work properly. So these type of errors may go unidentified by the checksum algorithm. So there we will have to find out an alternate. So that is one downfall of this particular checksum. And this algorithm is advantageous by the simple design and it is also easy to implement both at the transmitter side and as well as the receiver side. So I guess every one of you might have understood what exactly the error detection and error correction codes are, and then we have seen the concept of redundancy, and then we have listed what are all the various codes that are available for error detection and error correction, and we have discussed in detail about the parity bit. When looking at the parity bit, we have discussed one-dimensional parity and two-dimensional parity, and next topic we have discussed is the checksum, and in checksum we have discussed actually the transmitting algorithm and as well as the receiving algorithm of that particular checksum. So how checksum is included in the transmission frame. So that is all about today's video. So I'm going to see you in the next particular topic. So until then, happy learning.